Okay, anybody have any homework questions you'd like me to go over?
Number 4.
Yeah. Okay, so convert to miles per hour squared. Okay, so this is units number 4. And we're starting with negative 9.81 meters per second squared. And we want to convert that to miles per hour squared. Is that what it said? Miles per hour squared. Given the conversions, 1 mile is 1609.344 meters, and 1 hour is 3,600 seconds. Okay, so we're going to start with negative 9.81 meters divided by seconds times seconds. And I'm going to just start by first converting meters to miles. So I need to use the ratio, with this conversion here, I'm going to use the ratio that has meters in the denominator so that I can cancel these meters. So 1609.344 meters, and then 1 mile. And if you do the cancellations, you can see, okay, we're done with all that. We've converted lengths from meters to miles. So now let's go from seconds to hours. This time we need the seconds in our conversion factor to be in the numerator to cancel these. So we have 3,600 seconds over 1 hour. That cancels one of those. And then do it again because you can see we still have another second there we need to deal with. So 3,600 seconds over 1 hour. And might as well punch it out. So you get negative. You get negative 78,999.6 miles per hour squared. Any questions about that? Okay. Any other homework questions you want to see? Yes?
Just more of a general thing.
Yeah.
The due date for the assignment in D12 was set to the 17th or the 19th, even though it said it was due Monday.
Oh, okay.
That's like,
No, that's a total mistake. My other classes, I'm going to fix that right now. My other classes meet Monday, Wednesday, and Friday, so their assignments were due on Friday. So sorry about that. Okay, so now you can submit it through tomorrow at midnight. The due date it says is tonight at midnight. Let me do the other section too. Okay, any other homework questions? Yes.
Can you go over 8B?
Sure. Okay, 15.5 kilometers to millimeters. Okay, so we want to go 15.5 kilometers to millimeters. And to do this, you need to know that kilo, the K here, means times 10 to the third, and that milli means times 10 to the minus third. And by the way, when I give you tests and stuff, I'll give you every conversion factor, every conversion equation that you need, and I'll give you every meaning of any prefixes you need. So you don't have to remember that stuff. You just have to understand how it works. Okay, so in order to go from kilometers to millimeters, we have to go from kilometers to meters, and then meters to millimeters. So the step of going from kilometers to meters, that's the easy one. If you're just getting rid of a prefix, you can just replace it with its meaning. So this is equal to 15.5, and instead of writing the K, I'm going to write times 10 to the third, and then meters. So that's the first step. But now the second step is we're going to do it like a unit conversion. And in order to do that, we're trying to get to millimeters. So notice that I'm going to write like a conversion equation that says 1 millimeter is equal to 1. And now I'm going to replace the milli with its meaning. So 1 times 10 to the minus third meters. Okay? And now this is going to, my conversion factor is going to come from this equation. I want to cancel the unwanted units of meters in the numerator. So I want to put meters in the denominator. So I'm going to go 1 times 10 to the minus third meters in the denominator. 1 millimeter in the numerator. Those cancel. We're left with this. And so now we know we're done. We have the units we want. It's just a matter of doing the numbers now. We have 15.5 times 10 to the exponent rules say it's that exponent minus that exponent. So this is minus a negative 3. This is in millimeters. So that's the same as 15.5 times 10 to the 6 millimeters. And now to put it in scientific notation, we have one too many leading digit over here, right? So I want to divide what's on the left of that multiplication sign by 10. In order to do that and keep the whole number the same, that means I have to, I'm dividing this, so I have to multiply this one by 10. So I'm going to write this as 1.55 times 10 to the 7 millimeters. Any questions about that? And so really, part B of number 8 is, just like almost all of them in B, it's just a matter of what prefixes you're using. But what you're always hoping for is that you're going to go from something with a prefix to something without one, because that's just a simple replace. Any other homework problems anyone wants to see? Okay. Well, now that we're done talking about units, conversion, scientific notation, so we're going to go on to really, in a way, the first physics topic. And that is particle kinematics in 1D. So first, before we can get into the topic, we need to think about what this means. There's a lot of stuff in this title. So we have to talk about what a particle is, what kinematics means, and what 1D means. Okay. First, a particle. I think most people, if you asked them what a particle meant, they'd say a very small object. But that is not actually what it means. Really, what it means is it's a mathematical way of treating an object, and it works very well for small objects in a lot of cases, not as well for big objects, but you can treat anything like a particle. So remember that it's just a mathematical treatment. It's a way of modeling an object. And the treatment says the object does have mass. But we're treating it as having no length. And the entire object exists only at its center of mass. Basically, think of it as just the middle of the object. So center of mass. And since it has no length dimensions, there's no way to tell one side of it from another side of it. There's no way to say, okay, this is the headlight and this is the bumper or whatever. It all just exists at a point. And so it also has no orientation. There's no way to tell whether this object is facing up or facing down or left or right. Okay? So I think the best example of an object that is not tiny, that is regularly treated as a particle, is when people do calculations of gravitational effects, like planetary gravitation. They treat the planets as particles. Obviously, planets are gigantic things, but they don't care about the orientation of the planets. They just care about where it is, because that's what determines its gravitational effect on things. And so they treat these planets as if they only exist at the center, and they treat it like these tiny point masses are, moving around without worrying about when it's facing this way, when it's facing this way. Okay? So that's a particle. Later on, right towards the end, we'll get into doing calculations where we do treat objects as having length dimensions. And that means that the objects can spin, and you have to worry about what happens if it goes from being oriented this way to being oriented this way. The second thing we need to define is kinematics. And kinematics means describing the motion of an object without worrying about the causes of the motion. You can track the motion of a baseball as like someone hits a home run with a baseball. You can track its motion, and that's kinematics. What you're not doing with kinematics is figuring out what the force was that was required for the bat to hit the ball to make it do the thing. Okay, so you're just tracking this motion. Another way to think of it is it's the relationships between position, velocity, and acceleration without worrying about mass or force. Okay, so that's particles and kinematics. And then the last thing is 1D. What does 1D mean? For us, it just means motion along a line. It can mean it doesn't necessarily mean an object is moving along a line. Any object that at a given location only has the ability to move, it only has two choices of where to go from there, is a one-dimensional motion. So you could imagine a wire that's in some kind of funny shape and a bead that can slide along the wire. That bead is not moving in a line, but it is 1D because at any point it can either go this way along the wire or this way along the wire. Okay, so that's 1D motion. For us, though, we're just going to think of this as motion along a line. With our calculations and stuff, that's what we're going to deal with. And so the measurable quantities that we're going to discuss in this topic are position, and I'll always denote that with a lowercase p. Velocity, I'll denote that with a lowercase v. Acceleration, lowercase a. And the last one is time, and that'll be a lowercase t. And so the first thing I want to talk about is position. So we're just going to define position. And this is sort of the first place, like there's something kind of different about physics from other sciences, and that's how connected physics is to math. And in order to connect physical motions to math, you have to have some way, you have to have kind of a system in place for going from the stuff that happens in the real world, where people run and throw stuff and things bounce and whatever, and math world, where you have graphs and calculations and stuff. Okay, so I'm going to take a little time right now to talk about connecting the physical world to the math world and what that takes. Okay. So for position, let's say that we have an object that's in one-dimensional motion, so it's moving along this line. Let's say it's like a old-timey train, because I don't know how to draw the new trains yet. Okay, so this thing is moving along a line. And since we're treating this as a particle, remember, instead of this being a train that's 10 meters long or something, we're going to assume that it only exists at its center of mass. So that center of mass symbol, the symbol that you see on crash test dummies and commercials and stuff, that is the location of the train. Okay? But how do you go from the location of the train to a numerical position? How do you go from the train's location to its numerical position? Well, think about how you would, like, don't think about it mathematically. Just think about what you would do if you were looking at this train, you know, and somebody called you and said, "Where's this train?" Like, how would you tell them where it is? There would be two things you would give them. You would give them a reference, some kind of reference that they presumably know, you know, they know where this thing is, the 7-Eleven or the train depot or Lake Street or something, and you would give them a direction, okay? And if you orient them with a direction and you tell them a reference location, then you can tell them how far away the train is from there. Okay, so where's the train? And you say, oh, you know that 7-Eleven we were at last week? Go north 2 blocks and you'll see the train. Okay, well, in order to give a numerical position, you do the same things. You give a reference and you give a direction. And then you have enough information to give a position. So before you can determine this train's position, you need to choose two things. The first one is you need to choose a zero position. So we're going to choose the location in the real world of what we're going to call the zero position. Second, we have to choose the positive direction, just the direction that we're going to call positive. This also needs to be in the real world. We're doing one-dimensional motion motion along a line. And so the positive direction can only be two ways because one-dimensional motion only has two directions. So we can say positive is to the left or positive is to the right on this picture. So here is the path that the train is following. And I'm going to say this is the zero position. And then I'm going to say from that zero position, this is positive, and that means that this is negative. Okay, now that I've given that reference and that direction information, now we can measure meters from the zero and give a position. So let's say this is 1 meter, 2, 3, 4, 5, 6, maybe another half meter there. So that's 1 meter, 3 meters, 5 meters. So now at this instant, what's the position of that train? After we've chosen the zero position and positive direction, the position of the train then is equal to negative 6.5 meters. Are you with me on that? Well, what if I chose a totally different location in the real world to pop down the zero sticker and chose the opposite direction to be positive? Would I get the same position value? No, the position value totally depends on those two choices. The thing is, once you make those choices, everything depends on it, but if you're consistent throughout the problem with those choices, you can do meaningful calculations. Okay? So you make the choice of the zero position, the positive direction, and then you just keep that for the rest of the problem. Okay, the units for position have to be units of length. And so that means the SI units, the units we're going to use almost always for calculations, are meters. So anytime you give a position measurement, you're going to give it with units of meters. If you also choose an instant corresponding to time equals 0, you can plot an object's motion on a position versus time graph. You can think of this time 0 as like the instant that you start a stopwatch. Okay, you start it running. So if you start a stopwatch when the train leaves the station, okay, then you can look at the stopwatch at any instant and see how much time has elapsed, okay? All right, so let me do an example. So let's say at time equals 0, the object's position is negative 22 meters. When the stopwatch says 1 second, the object's position is negative 15 meters. When the stopwatch says 2 seconds, the position is negative 10 meters. And when it says 3 seconds, the position is negative 2 meters. So what would this look like on a position versus time graph? So I'm going to just draw out a graph. Position is always going to be on the y-axis. Time is always going to be on the x-axis. And we're going to have times 1 second, 2 seconds, 3 seconds. And the positions that we know are going to be negative. So let's see. Let's call this 5, negative 5, negative 10, negative 15, negative 20. So this is negative 22 meters. Okay, so at time equals 0, the position is negative 22 meters. At time 1 second, the position is negative 15 meters. At 2 seconds, the position is negative 10 meters. And at 3 seconds, the position is negative 2 meters here or something. Okay. We don't know what happens in between, so I'll just draw those as straight lines, but look something like that. One thing, we're going to see a lot of these position versus time graphs, and one thing to remember is there's no mathematical reason we couldn't have negative times, but we're just never going to use negative times. People just don't tend to use them in physics. And so you will never have anything show up on this side of a position versus time graph. Okay. That red hatched area represents negative times, and you won't ever see those. Anybody have any questions from that sort of introduction to this stuff? Okay, so this is a kind of problem that you're going to see now, and it's based on the stuff that we've just done. So let's do this example problem. So let's say here's the line that motion is happening along, and there's like a shed, and then there's a fire hydrant. Ooh, that was rad. I felt like a teacher for a second in one of those like dramatic teaching movies. I thought that was like my soundtrack.
What?
I don't know. Like what? Like what's what's that one called with Michelle Pfeiffer? Michelle Pfeiffer with the Coolio song? I don't know. I think I might be older than you guys.
That's a little before.
Yeah, exactly. It's before you guys were born. Okay, hold on. Let's look it up. I don't think it's supposed to be very good, actually, but
Dramatic teacher voice.
yeah. Yeah. It's a thing.
Thank you.
Okay, Michelle Pfeiffer teacher movie. Dangerous Minds.
Oh, I heard about that.
Okay. Well, you can find this and other movies at your local library.
Have you ever seen the movie Dramatic Teacher Voice?
It's a thing, believe me. Okay, so there's the shed, the fire hydrant, and then a car. Okay, and again, all of these are just represented by points. So that point, that point, that point. Okay. And between the shed and the fire hydrant, is 15 meters. And between the fire hydrant and the car is 10 meters. And so let's say that a person walks from the shed to the car. In 15 seconds. And then walks back to the fire hydrant in 10 more seconds. And we're going to plot a position versus time graph of this motion. But before we do that, we have to make choices of the zero position and the positive direction. So I'm going to just specify some choices for those. Okay, so I'm going to first say for part A, the zero position, so P equals 0 at the hydrant. The positive direction to the right. And time equals 0, the instant we start the stopwatch running, is at the start of the motion. Then second, we're going to draw a position versus time graph, but this time the position equals 0 is going to be at the car. The positive direction is going to be to the left. And time equals 0. The stopwatch, we're going to turn the stopwatch on 5 seconds before the motion starts. Okay, so I am going to take this. Um, okay, so this is the motion. And for part A, I'm going to look at these things and I'm going to label them on this figure. Okay, so you can imagine I have a position equals 0 sticker and I'm going to put it somewhere on the ground, somewhere in the real world. And then I have a arrow pointing in the positive direction and I'm going to set that down one way or the other. Position equals 0 is at the hydrant. So all of the stuff that is specific to this part of the problem, I'm going to put in green. So here's our 0. Our positive direction is to the right. So positive is this way, negative is this way. Now that I've done that, I can label all of the different positions of the objects. So if you start at 0 and go 10 meters in the positive direction, what's the numeric label for the car? So think of on a number line, if you start at 0 and go 10 in the positive direction, what number are you at on the number line? 10, right? So here we're at positive 10 meters. And now let's go back to the shed. If you start at 0 and go 15 meters in the negative direction, what are you at? Yep, negative 15. And now I'm going to draw the motion. So the motion starts at the shed, goes to the car, back to the fire hydrant. So starts at the shed, goes this way until gets to the car, and then goes back to the hydrant. From this instant to this instant takes 15 seconds. And from this instant to this instant takes 10 seconds. And so now I can start to think about the times corresponding to these instants. I said that for part A, time equals 0 is when the motion starts. So that means that right here, the stopwatch says 0 seconds. Okay, right when the person leaves the shed. Okay. If it says 0 seconds when the person leaves the shed and it takes 15 seconds for the person to get to the car, what does the stopwatch say when the person gets to the car? 15. Yep, 15. And if it takes 10 more seconds to get back to the fire hydrant, what does the stopwatch say there? 25, yep. Okay, so now we have these instants and we could just read off the graph what the time and position are. At the instant the person leaves the shed, time is 0 and position is negative 15. When the person gets to the car, time is 15 seconds and position is positive 10. When the person gets here, time is 25 seconds and position is 0. And so now you're just plotting those out. I'll do it as a little, I'll write out a little table because I think this is a nice way to not get confused about it. But so all I'm doing is looking instant by instant. The first one is at 0 seconds and the position is negative 15 meters. The second one is 15 seconds and positive 10 meters. And the third one is 25 seconds and 0 meters. And if you plot this, the times that matter are 0, 15, and 25. And the positions are negative 15, 0, and positive 10. So the first point is 0 time negative 15 position. The second instant is 15 time positive 10 position. And the third one is 25 time 0 position. And if you connect these points with straight lines, it looks something like that. We'll find out later that no motion really is just straight lines like this, but for now, you can just treat it like it is. Okay. Any questions about that one? Okay, let's do part B now. And I'm going to start with this same, this same diagram. Okay. And we're going to start labeling stuff based on the 0 position in the positive direction. For part B, I said the 0 position is going to be the car, and the positive direction is to the left. Okay, so this time, 0 position is there. Positive is this way, which means negative would be this way. If you start at 0 and go 10 meters in the positive direction, where would you be? Yep, positive 10. And now if you start at positive 10 and go another 15 meters in the positive direction, where would you be here? 25, yep. Now the motion of the person is no different than it was before. The person still starts at the shed, goes to the car, and then goes back to the hydrant. And it's still 15 seconds from the shed to the car, and it's still 10 seconds from the car to the hydrant. But this time, we were told that you actually start the stopwatch before the motion starts. So you start the stopwatch 5 seconds before the motion starts. So you click it on, you wait 5 seconds, and then the person starts moving when the stopwatch says 5 seconds. Okay? So this happens at 5 seconds. Then based on that, what does the stopwatch say when the person reaches the car? I didn't hear what you said, but I'm going to assume it was 20. Good job. And then what does the stopwatch say when you get to the hydrant? 30. Yep. And so again, we can just fill this out like a table. At that first instant, the time is 5 seconds. The position is 25 meters. At the second instant, the time is 20 seconds, and the position is 0. And at the third instant, the time is 30 seconds, and the position is 10 meters. So based on that table, the times we're going to care about are 5 seconds, 20, and 30. So let's say this is 5 seconds. This is 20 seconds. And this is 30 seconds. The positions are 25, 0, and 10. And now you can just read those off the table. The first point is 5 seconds, 25 meters. The second one is 20 seconds, 0. And the third one is 30 seconds, 10. Any questions about that? So it's the exact same motion, but with different choices of zeros and positive direction. You can see that the graph looks different. It's shifted up and down, it's shifted left and right, and it's flipped upside down. Okay. But so this is kind of the process that, you know, as we go on, doing this is going to get very comfortable. But this is what's always going to be going on in the back of your mind when you start connecting a motion in the real world to its mathematical labeling. You know, you're going to be thinking, okay, what's the 0 position? What's the positive direction? What's the 0 time? Let's just do one more of these. And so I'm going to write a problem like this up here, and then I'm just going to give you a little time to try to think through it. So let's say this object's moving along this line. There are 3 points, A, B, and C. The distance between A and B is 1 meter, and between B and C is 3 meters. And let's say that the motion starts at B, takes 2 seconds to get to C, and then 5 seconds to get back to A. So this is 2 seconds, this is 5 more seconds. Can everyone understand that diagram? So now let's say we're going to choose our 0 position at C, the positive direction to the right, and time equals 0 is going to be at the start of the motion. And you want to draw a position versus time graph. Okay, so you can do this however you want. If it makes sense to you to do it another way, feel free. But I think an easy way to I mean, a good way to approach it is to label the times at the 3 instants of the motion, and then draw a label of the position equals 0 in the positive direction, and then label the positions of those points. And then you can just start sort of reading those values off as you put it into a table. So take a few minutes, see if you can think through this. Feel free to talk to each other or compare answers or ask me questions if you get stuck. And after I give you a few minutes to work on it, I'll go through it and you can compare your answers to what I did. Let's go. Hold on a sec. Okay. So first, let's label the times. What does the stopwatch say at these 3 instants? What does it say when the motion starts? 0, yep. What does it say when you get to C? 2, perfect. And what does it say when you get to A? 7, yep. And then the 0 position is at C, so this is 0. And the positive is this way, which means negative is this way. So what's the position label at B? Negative 3, perfect. And what's the position label at A? Negative 4, that's right. If you're already at negative 3 and you go another meter in the negative direction, right, negative 4. Okay, so now I guess what you have left is we'll fill out this table. So what's the first pair of coordinates representing that first instant here? Yeah, 0 seconds, negative 3 position, meters position. And then the second one,
2, 0.
Yep, 2, and then 0 meters. And the third one, 7 seconds, negative 4. And so now, now it's just a matter of plotting these points you've come up with. You have 0, 2 seconds, 7 seconds. And for positions, you have 0, negative 3, negative 4. The first point is 0, negative 3. The second one is 2, 0. And the third one is 7, negative 4. Anybody have any questions about that process? Okay, so that's it for today. On Wednesday, we'll talk about velocity and acceleration. For the assignment that I'll give you today, it'll be a couple of things like this. Okay, see you Wednesday. Oh no, wait. We have lab this week. So half of you I'll see in 20 minutes next door, or 2 doors down.
The classroom number?
S1324, and this is 28.